Hey everyone, welcome back to our YouTube channel Becoming a ROS Developer. I'm Desire, and today we've got Dahlen, who just completed the course Linux Basics, and will be giving us a presentation of that. So first of all, we'll begin by seeing his code base running on the real robot so that we can first see how it works, and then we can get into the details of his code base, what he did, and then after that, we'll get to ask him a couple of questions or ask him as we go. So without any further ado, let me now hand over the platform to him so he can begin his presentation. All right, whenever you're ready, Dahlen.
So now I've just used the bring up command, but it's been disconnected. Sometimes there's a little issue.
Mm-hmm.
So now the visualization software has booted. And so I made a mistake. I'm supposed to link to the real robot first, then use the bring up command.
Mm-hmm. Okay.
And that is loading now. Might have to redo the bring up command. Real robot session is going live. Here's both views. And let me just see the status of the web shell. So yes, I need to redo the bring up command. Now let's load my code. So first you want to load the robot interface code that was provided by the course. This
Mm-hmm.
allows your code to interface with the robot, but you need to use a separate web shell because the first one is running the bring up command linking my computer to the robot. So let's change the directory to where the robot interface Python code is. That's done. Now let's load up the interface. That's running. Takes 5 seconds to get ready. You want to wait for it to get ready. And now it's ready. It's printed. So then now we're going to run the actual pathfinding algorithm, the obstacle avoider, first in
Mm-hmm.
a separate web shell. My internet is failing. Okay, maybe it can stabilize. Let's change the directory to where the code is. Now we're there. Now we're going to load the bash scripts. And after this, the robot will start moving and hopefully avoid every obstacle.
All right. All right.
So then this is a problem that happens uh, frequently. So then the permission to execute has been removed from the bash script. So to check the permissions, we're going to run this code and it'll show me which codes are able to execute. So the simple patrol, robot statistics, robot interface, robot functions, but the obstacle avoider does not have the X, which is the execute permission, only has read and write for the owner, and
Mm-hmm.
then only read and read for the group and all others.
Yeah.
So let's change that. Let's change modifications, change permission. And a simple way to do that is just to do +X, which will allow all users to execute
Yeah.
the program. You also can use the numeric codes, but
Yes.
this is what I'm going to use for now. Just make sure I typed it right. Obstacle avoider.bash. And then we can just double check to see if the permissions have changed. And as you can see, obstacle avoider is now in green,
Mm-hmm.
meaning it has permission to execute for all users.
Yes.
Now we can run the code and think it's still in my clipboard. Yes, it is. So now it's running, and Control C will terminate the code. Make sure. So yes, the Python interface is still going, and this code is still going. Maybe a slight error with the visualization. Okay, and the visualization's working.
Okay.
The robot's moving. It's encountered an obstacle,
Right.
and we're going to load another bash script just to get some data from the sensors. It's going to be the same, similar procedure. Change the directory to the proper one. Now load this script, which will tell us some data collected from the sensors.
Okay. You probably need to move every other terminal or window that's covering the camera view so that we can really see
Try
what
to
it's doing.
find a
Yeah.
better place for these windows.
Yeah, I think that side is much better. At least we can see one completely clear with no.
Oh, okay, yeah.
Yeah.
And let's so this view is unobstructed.
Yep.
This view is
Yeah.
slightly obstructed.
No worries. No worries. Yeah, I think one is fine. One is fine for now. Yeah.
Okay, and then so yeah, it's encountered another obstacle. It's moving based on the 8 if statements that I wrote uh, under the direction of the course description. It's now looking for a clear path to miss this pole on the ground. It's taking a little while. Unfortunately, my code was not optimized, and there's a little bit of delay because of the distance. It's encountered another obstacle. It will move. Oh, so this something to improve upon would be to add a favor to where it's more clear. So now it moved right instead of left.
So
And
right now, how does it make the choice between left and right? Is it randomly or?
oh, so yeah, it favors clockwise, so that's why it moves. That's how it finds its direction.
Okay, so
But
I'm guessing in the loop, whichever comes first, right? Between choosing right
yeah,
or left. Okay, all right.
and I can load up the script now.
It's fine. Let's see what it
Oh,
does in
okay.
front of this obstacle for now, and then we can get into the code later.
Okay.
So just want to let it avoid a couple more obstacles first, and then we can.
So I'm assuming that the right sensor was interacting with this obstacle. That's why it chose not to go straight then.
You mean
It
the
wants to
right
be
laser
clear.
index?
Yes.
Okay.
And it's going here.
Okay. And what threshold value is the robot using? What's the maximum? What can I say? Maximum distance that it can get close to an obstacle?
I believe it's 1 foot, I believe. Not sure the scale from the sensor. From what I believed, I used 0.3 meters,
Okay. All right.
which is
About
1 foot.
a foot. Yeah.
How large is the turtle bot? I'm not sure. I've always seen it through
Through the camera.
yeah. So here it was free to move forward, but it encountered an obstacle on the left. It wants either all three, so the right and the left to be clear
Uh huh.
and front to be clear. or it wants the right and the left to have obstacles and then the front to be clear.
Oh,
But if there's only an obstacle on the left side or the right side, it'll turn until it's either all clear in front, left, and right, or only clear in front and obstacles on both left and right.
okay. So it
So
doesn't. So based on your algorithm, it doesn't really mind whether one is free, right? There is no points where it has to take into consideration whether the index next to it, for example, the front left, for example, and the front.
yes,
So it at some point it can just rely on one index to say, okay, if front is free, I'll keep going forward.
correct.
Okay.
But if front and right are free, then it'll move. It'll turn until all three are free or only front is free.
Okay. If you encountered an instance where front left is free, or let me say front left is blocked and front right is blocked, and the passage was not wide enough for it to fit.
That is a good question. I could load up the teleop, the keyboard control, and then put it in that situation if
No,
you want.
I just want you to think about it as in hypothetically,
Okay.
like, what do you think would happen? Did you get to think about that when you were developing your obstacle avoidance algorithm? Um, Based on the sectors, right, and the threshold distance
Okay.
that we've got, right, would it
Right.
fit between those two obstacles?
So yeah, so I assumed that zero point 0.3 meters clear would allow it to move and with the space available,
Mm.
and there's a sleep command to make sure it doesn't overshoot and accidentally hit an obstacle.
Yeah.
So right now the front is blocked and right is free and front left is free, so it's going to continue to turn.
Uh huh.
So
Okay.
now front left is blocked, front is free, and front right is free. So it's going to turn again.
Mm.
And it
What?
may seem like efficiency, but if it had gone forward, then it would have hit the obstacle, the turn signal there.
Yeah.
So
What?
this extra turn did provide an obstacle avoidance
Uh huh. Okay. All right.
offering.
Why I'm asking about this is sometimes if we, for example, in your case, right, you're not quite aware of the exact dimensions of the robot, right?
Right.
So the threshold distance determines actually determines how much clearance it's going to have when it rotates to get the obstacle out of its way, right? So
Right.
sometimes if your threshold is too small, for example, you have, let's say, 0.18, for example, right? Or let's just say 0.1 to make it very small. You'd realize that the robot will get too close to the obstacle, and when it tries to rotate, it cannot rotate to get it out of its way because then it touches in the process of rotation.
Correct.
Yes. So it's very important to understand what the threshold distance is doing for you. That's why I posed the question: had you encountered a case where you had both the flanks being free, I mean being occluded, but the front is saying it's clear to go, and then it would touch obstacles. But yeah, I think just food for thought. Can you
Yes.
show the script itself now so that we can discuss in more detail?
Okay. Would you like me to open the IDE?
Yes, please. I think if you can even stop the robot for now. So,
Okay, so let's.
or maybe just disconnect. I think most likely we'll run it in simulation after this. So just to for good measure.
Okay. So we'll end the connection. This will kill bring up, and then you can end the real robot session.
Okay.
here's the IDE.
Okay. So I think let's start with the obstacle avoidance first. So the script that is responsible for that.
So this is obstacle avoidance is my path finding algorithm, or at least obstacle avoidance path finding. So we have the left range. So for this while loop, we've sourced the robot functions.bash was a previous script. Just gets and sets different variables, and then from these variables we initialize linear velocity and angular velocity. And now this is where we print out these different ranges that the sensors are collecting from obstacles in the arena. And then this is just another check to make sure that it's less than the threshold. And the threshold, as we discussed earlier, is 0.3 meters. The units aren't meters, so 0.3 meters, technically 1 foot, close to. And then here's where the obstacle avoidance begins, the 8 if statements. So 1, if front left is not free, front is not free, and front right is not free, so these are all blocked, then this is the if statement using that logic. Then we want it to turn left if the left range, so the range from the sensor, is greater distance than what the right range is getting. We want it to turn left at this angular velocity is roughly 1/10 of pi, or it's pi over 10. And then to the left, and then for the right it's the same thing but in the opposite, so the negative pi over 10 to go that direction. And then that's the end of this if statement if they're all blocked, if all 3 are blocked. And then this is an else if, so if front left is not okay, it's all right. So if you, with regards to this, right, if you swap the order in which these Boolean values are being checked, right, in what way do you think it would affect your robot? For example, I would give like context to this question. So you remember the case where you said it prefers to rotate clockwise, right, instead of counterclockwise. Right.
Is that right? Yes. Right. So if you wanted it to rotate, to prefer the opposite, which is counterclockwise, what would you change? Like, do you think you would have to change this specific or the order of this if statement and else if?
My personal opinion, I don't think this statement would affect it too much, because I think the happenstance of all 3 sensors being blocked doesn't come, at least from seeing the arena, it doesn't happen that much. Usually it's 1 is or 2 are free, the left and the front, or the front and the left. But definitely switching this order and checking the right range first would ignore the else statement, which would, I would think, give preference to the other rotation, just because there could be a slight discrepancy and maybe the numbers could be very close, and since they're float points, they could be it could just take that one and since
because so I think it's it's very difficult to tell, right? Because it also depends on how fast the loop is executing, right? So what if in the process of rotation it goes through so many cycles, right? Then you cannot be able to tell which branch will be chosen. So I was trying to probe you to think in that line, but even though it's difficult to predict right now, given the fact that it might be executing at either a very high frequency or a very low frequency, but yeah, something we can think about.
Yeah.
But all right, let's go on. You can continue with your explanation for this.
So then my second statement. So front left is not free, front is not free, but front right is free.
Mm.
So since front right is free and all the front and the left are blocked, the most logical course of action would be to turn right.
Mm.
So at the same angular speed, we'll turn right, we'll sleep for 1.5 seconds, give the robot enough time to turn, make
Mm-hmm.
sure another command doesn't overwrite the turn to make it a shorter turn, and we'll reset the angular velocity to 0 just to ensure that the robot doesn't overshoot the turn.
Mm-hmm. How do
And then,
you, so the choice of value, right? So that's the time of rotation or the sleep value. Did you just pick that from like the helper scripts that you're given, or you had to try it out?
so if I did it faster, I noticed that it would change too much. The provided value was, I don't want to say optimal, but it was sufficient and not in avoiding the obstacles, which I noticed,
Hmm.
and it was more predictable. So it was easier to gauge instead of, as
Yep.
you can see in the real robot session, the turns were not gradual, even so somewhat of a, it would have been nice to maybe increase it a little bit because as you see, sometimes it would turn and then it would turn again.
Yes.
So the
Yes.
turn wasn't fully optimized, but that lack of efficiency does prevent errors to take advantage because maybe a smaller turn is needed.
Yes. That's.
So more more sensor gathering would be needed since okay, maybe this is only a small turn,
Mm-hmm.
or maybe do a large turn would help this robot navigate faster.
Okay. So
But
you.
this small turn,
I see. I
yeah.
see. So you're speaking in with regards to maybe taking into consideration. Right now you were using how many sectors? Eight, right? Like
Yes.
eight laser indexes. So if you were to use 16, it would be better. Is that where you're going with this?
Yes, it's with the logic as well. So I have to use the logic to make sure that okay, so the turn needed is only a smaller turn, or the
Yes.
turn needed is large, depending on how many sensors are blocked.
Uh-huh.
So that would definitely have an impact, which is why I decided to stay with just the pi over 10
Okay.
because it it prevented collisions with obstacles, which I believe was the prime objective.
Yes, true.
However, it was quite slow, so it does need some optimization.
Yeah, yeah, yeah. It's a good thing you did notice these things, and also it that's the whole point, right? If you can realize the limitations of what you're already working with, and be able to predict or at least have some thought process that leads to how you can improve it. So it's quite nice. It shows that there has been some very good thought that has gone into the algorithm itself. So yeah, I think well done on that. Um, you can
Yeah.
proceed with this script if there are other little bits that you would speak
So this
about.
one is a little bit more complicated than the other ones. So again, front left is not free, but front is free,
Mm-hmm.
and front right is not free. So this one is kind of the example of let's say you're two dividers, and then but the front is free. So this in
Yes.
situation you do want to move forward, even
Yeah.
though the left and the right are blocked.
Mm-hmm.
The
Mm.
front path is clear. This kind of symbolizes like a highway or some type of pathway.
Yes.
You would
Yes.
want to proceed, you wouldn't want to stop. So we calculated a distance to move based on what the front range was getting
Mm-hmm.
minus the threshold. This was the distance to move. We don't want it to move too far because just because it's free for the immediate range doesn't mean it's going to be free permanently. So then I decided to go with point 0.1 meters per second. It seems reasonable speed and prevented any hard braking for the robot. And then also we would sleep for however much the time to move equation calculated. So then it was the distance to move divided by point 0.1,
Mm-hmm.
which would give it 10 times more than the distance to move. So whatever the distance to move was, we'll move that time multiplied by 10 or divided by point 0.1,
Mm-hmm. Okay.
and then
Okay.
sleep. And then time to move is again is manipulated because this number is a little bit too large. So you subtract, okay, so this is ended. You subtract 1 second to kind of make it within the limits because there's a delay. So you have to account for the delay. And then there's also, time for the robot to react. So to account for this, you shorten the time to move by 1 second. And then you just print out moving forward so the robot, the user can know what the robot's doing, what code is being executed, and then reset the linear velocity to 0. And that would be the end of the if statement. If left and right are blocked, but front is free. This is the movement forward algorithm. And then this one is similar to what we've discussed before, but again, front left is not free, front is free, and front right is free. So this is front is free and front right are free, but not left. So we want to turn right to either align it to be front right and front left are not free, so that we're in a thoroughfare, or all three are being free, which will be another movement forward algorithm or if statement that we'll see coming up. This was pretty simple. Just turn right at the before distinct angular velocity, and again sleep for 1.5 seconds. Perhaps this sleep could be optimized for a little bit shorter. As we saw, the robot was a little static more than we would like, but this is for safety. And then set back the angular velocity to 0. So then now this one is front is not free, front right is not free, but front left is free. So that means we need to turn left. So similar to the above, but except for the left. This one, front left is free, front is not free, and front. So this one is where another decision needs to be made, because left is free and right is free, but front is not free.
Yes.
So we need to distinguish. Again, I chose if left is first, but this could be
the opposite.
This could be the opposite, and this gives it somewhat of a bias.
Okay.
So,
All right. I think for now it's very good details. So I'll just give you about a minute or so to just run through the robot statistics script, and then I think we should wrap it up after that.
And then, of course, we use the robot functions bash, where they get the getter and setter functions. This is where we're going to get all of these data from, and then now we could use this while loop to print out the distance covered by getting the odometry distance, which is provided from the robot interface. And the robot functions bash calls the robot interface. This is where, no, it doesn't. This is just providing the access point. The robot interface is running in the background. So then the yaw, this is not too relevant for this, since we're moving in a 2D plane. This is more for a object that is floating in XYZ space, not just XY, but it's provided just because it could, the robot could fall over, become unstable if on one wheel. And then the IMU, the inertial movement unit, provides angular velocity, and then linear acceleration is provided by the IMU as well. So in essence, really what we're getting from the robot statistics is distance covered, the direction, these are the most important, and then the LDOM position X and Y is just the direction, so more
all right.
important to this.
All right. Thank you very much, Dahlen. Wonderful presentation. So thank you for taking us through how you develop the scripts. So I think without further ado, Alright everyone, this was Dahlen's presentation, and congratulations to him. I would like to thank him for giving us the detailed explanation and his way of making decisions towards having the robot perform the way it did. So I would like to encourage all those of you who would like to give a shot to some of the courses that we offer certification on to do so, and you can come and showcase your work. So without any more of taking your time, I'd like to say keep pushing your ROS learning, and bye bye.